This is a video on Jacobians. The question states, let R be the region bounded by the parallelogram with vertices 0, 0, 2, 1, 1, 2, and negative 1, 1. Evaluate the double integral over R of 2x minus 4y times e to the x plus y dA. So let's start by sketching a picture. I have my vertices 0, 0, 2, 1, 1, 2, and negative 1, 1. And I see I have a parallelogram. And it's convenient to find the equations of the lines that form this parallelogram. And I did that. This first line has form x minus 2y equals 0. And when we're working with this Jacobian topic, it's easier to write it in standard form, where we have ax plus by equals a constant, than it is to write it in y equals mx plus b. And we'll see that in a minute. This next line is x plus y equals 3, and the third line is x minus 2y equals negative 3, and the fourth line is x plus y equals 0. So again, I just had 2 points, and I used the standard formulas to find the equation of a line using 2 points. So I'll let you work that out yourself, but that's what I got. What's nice about this is that this helps us decide what u and v are for our change of variables. So I'm going to set u equal x plus y so that this line here becomes u equals 0, and this line here becomes u equals 3. And I'm going to let v be x minus 2y. So this line becomes v equals 0, and this line becomes v equals negative 3. And that's nice because in the uv plane, this parallelogram transforms into a rectangle, and actually a square, so that u goes from 0 to 3, and v goes from negative 3 to 0. And it's much easier to integrate over a rectangle compared to integrating over a parallelogram. So now in the change of variable theorem, it tells us I need to calculate the Jacobian. And remember, the Jacobian is defined by this del xy over del uv. And since we have u and v as functions of x and y, it's a little bit easier to use this formula that says that del xy over del uv is 1 over del uv over del xy. So we calculate that, and recall that's the determinant of this matrix. So we have 1 over the determinant of the matrix of partial derivatives, u sub x, u sub y, v sub x, v sub y. So we can calculate u sub x is just a partial derivative of u with respect to x, and that's 1. U sub y is also 1. V sub x is also 1. And v sub y is negative 2. So I get 1 over the determinant of the matrix, 1, 1, 1, negative 2. And I take that determinant, 1 times negative 2 minus 1 times 1 is negative 3. So I get 1 over negative 3, or negative 1/3. So now I'm ready to use a change of variable theorem that tells us that a double integral over a region of a function of xy dA is equal to the double integral over the transformed region in the uv plane of the function of u and v times the absolute value of the Jacobian times dA. So 2x minus 4y, well, that's just twice x minus 2y, or twice v. So I write 2v. E to the x plus y, well, x plus y is u, so that's e to the u. Then I have the absolute value of the Jacobian, or the absolute value of negative 1/3, dv du, and v is just going from negative 3 to 0, and u is going from 0 to 3. And that's because I have a rectangle here. Makes the limits so nice. So I calculate this out. I could do this by hand. It's not that hard. And what I got was that this double integral, which is the double integral of our original also, is equal to 9 minus 9 divided by e cubed. And I'm done with the problem.